about implicit differentiation. Okay, I'm going to say that the circle is a relation but not a function. I should say the equation of a circle, but you know what I mean. So in other words, we cannot express y as an explicit function of x. Okay, here's the general equation of the circle. In general, we have the following. The equation of the circle will be x minus a squared plus y minus b squared equals r squared. And this is a circle with radius r and center at a, b. Okay. All right, let's do this. In order to simplify stuff, we're going to let the center of the circle A, B, B, 0, 0 at the origin, right? Then we're going to end up having x squared plus y squared equals r squared, which we're all familiar with. Okay, so what happened is, here's the circle. It's not an easy thing to draw a circle. So this is a circle with radius r at the origin, but instead of dealing with this relation, x squared plus y squared equal r squared, we're going to break it down into two halves. The first half, we're going to have simply half a circle like so. Okay, and this we call it y1. So this is y1 equal f of x, and we can do it because half a circle passes the vertical line test, so it is a function. And then the second half will be underneath like so. You're going to say this will be y2 equals, so this will be f1, and y2 equal f2 of x, like so. So we do have now two pieces. Each piece by itself is a function. Okay, and in the circle, we're going to be this plus that. Okay. So each half of the circle can be expressed as a function. And we're going to say that y1 equals the positive or the principal root of r squared minus x squared equals the top half, and y2 equals the negative square root of r squared minus x squared equals the bottom half. Okay, and now we can start taking the derivative. If we want to find the y dx, then depends whether we're looking at the top half or not. Okay, so if we want to calculate or to evaluate dy dx, then we do it by half. So we need to treat 1/2 at a time. Okay, so dy1 dx will be, we take the derivative and you do a little chain rule, r squared minus x squared, let's say equals u, so du dx equals 2x, right, or negative 2x, so you end up having, and then you take the derivative of the square root of u, which is negative 1 over u squared, so you end up having negative 2x, so it will be like so, 1 over the square root of r squared minus x squared, right, and then times negative of 2x, the derivative of x squared. So you end up having negative 2x over the square root of r squared minus x squared. And what about the bottom half? Well, the bottom half, dy dx, remember the bottom is negative up front, so again it will be negative 1 over the square root, and then multiply by the derivative of negative x squared times negative 2x, so it will be the same thing but positive. And now you can check and see if it passes the common sense. Notice that the derivative of the top is negative. And if you look carefully, let's take you can test it on the first quadrant. Okay? What happened to the tangent, the slope of the tangent in the first quadrant? Is it positive or negative? Speak. It's negative, right? You pick up a point in the first quadrant and the slope is negative. On the other hand, you pick up a point in the bottom half, in this will be the fourth quadrant, you'll see that the derivative is positive. So when x is positive, the derivative is negative for the top half. When x is positive, the derivative is positive for the bottom half. So it does pass the common sense test. But this is an inefficient way to find the derivative of the circle. Okay, so what would be a more efficient way? What we did here, notice that we end up writing two explicit functions. y1 equal an explicit function of x, and y2 equals an explicit function of x. Instead of dealing with 1/2 at a time, we can do something that is called implicit differentiation. We take the relation x squared plus y squared equal r squared. Remember, this is a relation, it's not a function. And you know what? Let's take the derivative of both sides of the relation, see what comes out of it. Okay, so let's see how this works out on the next page. So here it comes on page, this will be already page 4. Okay, it is easier, as I said, it is easier to find or to evaluate dy dx of a relation by something we call implicit differentiation. So we accomplish that by we differentiate both sides of the relation with respect to x. So we differentiate the relation. In this case, it will be x squared plus y squared equals r squared with respect to x. Notice that I specify with respect to x. Can you tell me why it is important to specify, to include this in the statement? What are the variables of the relation? Speak, people, speak. Call it out.
X, Y, and R.
X and Y. R is not a variable. R is a constant. That's the radius. But the variables are X and Y. For a given R, you have different values of X and different values of Y. So it's very important to specify that you take the derivative, you differentiate with respect to what variable. Because we want dy dx, that's what we're after, we take the derivative with respect to x, so we differentiate with respect to x. Okay? One of the things that you see in implicit differentiation, we're going to use the chain rule. And if we want y, if you have y as a function of x, then you do something, you differentiate your relation with respect to y, and immediately use the chain rule to do dy dx, to multiply by the derivative of y with respect to x. And this is what we are looking for. All right, let's do an example here, okay? So let's see how it works out. Here's an example given the circle. X squared plus y squared equals 64, right? And find dy dx. Okay, so implicit differentiation tells us to do the following. That's a long word, implicit differentiation. I think that's the last time I'm going to write it. Take the whole relation d dx and take the whole relation, x squared plus y squared equals 64, and take the derivative with respect to x of everything, including the equal sign in the middle. Of course, the equal sign in the middle is going to remain equal. So let's see what comes out of this. Now pay close attention. This is the first time you are seeing something like that. So catch it early so it will settle in your brain correctly. Okay? What is the derivative of x squared? 2x. What is the derivative of y squared? 2y, but this is the derivative of y squared with respect to y. We want the derivative of y squared with respect to x. So what does the chain rule tell us? It's d dy times dy dx, right? And what is the derivative of y with respect to x? We don't know. It's y prime. Matter of fact, that's what we want to find. Okay? And again, this is the fun part. You can take the derivative of y squared with respect to x. You first differentiate it with respect to y. So it's 2y. And then you differentiate it with respect to x. Why? Because of the chain rule. So it's 2y times dy dx. Okay? Let me write it as dy dx for the first time. Okay, on the right side, what is the derivative of 64? Folks, what is the derivative of 64? 0. It's a constant. And that's it. We can now divide everything by 2 and get y times dy dx equals negative x. And dy dx is simply negative x over y. And we are done. Isn't it a beauty? That's it. We are done. How this compare to the earlier result? This is the same thing as the earlier result. Think about it. Okay? It's the same thing. Spike, let me just make a point here. If you think about it, if y is on the top half, then y equals the positive square root of r squared, or 64 minus x squared, right? So, okay, I need to think for a second, so I'll pause here, take your question, Mike.
No, you made me thinking about the question. I'm trying to figure out how you got that. The 2x over the negative 2x, 2x over.
Okay, the derivative of x squared is 2x.
No, I meant on the other page.
On the other page?
Yeah, when you did half, you were differentiating half.
There is, okay, this is where I screwed up. This is 1/2, this is 2, and this is 2. And the 2 and 2 cancel out. So that's also, this is the mistake I made. Remember, the derivative of 1 over, the derivative of square root of u is negative 1 over 2 square root of u. And I missed that part. So there is no 2 here, and there is no 2 here. Okay? And I just realized that as soon as I was comparing the result of the implicit differentiation to the new result, I realized that I had something that doesn't add up. Okay? So make sure to correct this in your notes, please. And now what I want to do is verify the result. So if I find my pen, I can continue. If not, class is over, I can find my pen. All right, here we go. Let's look at the top half. For the top half, y equals the positive square root of 64 minus x squared, right? So dy dx would be equals to negative x, right, over the square root of 64 minus x squared. The bottom half y equal negative square root of 64 minus x squared. So for the bottom half, dy dx will be negative x divided by negative square root of 64 minus x squared, and because of the double negative, we end up having positive x over the square root of 64 minus x squared. And this conforms to the result we obtained before by doing explicit differentiation. All right? So, but notice how nicer to write the derivative in this term. And to follow up with an example, given the same circle, x squared plus y squared equals 64, evaluate dy dx when x equals 4, like so. Okay, that's one of the ways to write it. Okay, so from the previous example, we have negative x over y. Okay? Now, we need to find out the value of y, right? So we're going to substitute I'm going to substitute x equal 4 in x squared plus y squared equals 64. Or so we get 16 plus y squared equals 64, or y squared equals 64 minus 16, which happened to be, I think, what? Happened to be 48. Right? So y squared equals 48. It's not a perfect square, so we need to do something about it. But not to worry, because if y squared equals 48, then y equals plus or minus the square root. 48 has 16 as a perfect square, right? So the square root of 16 times square root of 3, or 4 square root of 3, like so. Now, plus, of course, will be the top half, minus will be the bottom half, and now we have the points. So we have 2 points. We have 2 points that correspond to x equals 4. That's why the circle is not a function, right? It doesn't have this uniqueness. So we have 4 and 4 square root of 3. And also we have 4 and negative 4 square root of 3. So those are the 2 points on the circle, one on the top half, the other one on the bottom half. So, top half, we have dy dx equals, remember, it's negative x over y, so it will be a negative x, which is negative 4 over 4 square root of 3, or simply a negative 1 over square root of 3. And bottom half, the derivative at the bottom half will be d dx, and here we have negative 4 divided by negative 4 square root of 3, and we know to expect a positive value. Okay? So those are the 2 specific results. So one thing that you're going to realize when you work with implicit differentiation, you try to find the derivative at a certain value of x, you need to come up with the point. So you need to calculate the value of y as well, because in the result of implicit differentiation, if you look right here, you'll have both x and y as part of the derivative. So you need to come up with a value for y in addition to the value of x. Okay?